Now let's talk about the decorations in knot-Floer homology. For knot-Floer homology, in order to induce maps on HFK', we need some decorations on the cobordism. The decoration consists of a set of arcs with endpoints consisting of 2 points on each end, so on each knot at the end of the cobordism. And in order to induce well-defined maps, these arcs must divide the surface into orientable pieces. So in the orientable case, where you have an orientable surface, we can just take a pair of parallel arcs running from one end to the other. And since the surface is already orientable, like all the pieces are going to be orientable, implicitly this is what we were doing in the argument before. But in the non-orientable case, in order to divide the surface into orientable pieces, the arcs have to entwine this non-orientable tube. So here's the picture of the vertical big cylinder it's going to be the knot times the interval, so k times I cylinder, and then we have this sort of non-orientable tube you can see it as a tube with like a little flip in the middle. And in order for these arcs to cut the surface into orientable pieces, they have to go through this non-orientable tube. In this situation, so like that means that when we define our cobordism induced maps, we're sort of taking this decoration going through the tube. But in this case, actually, the tube cutting formula is also like maybe not a tube cutting formula, but like you end up getting the same tube cutting formula. And the reasoning goes like this. So one thing you can sort of show directly is that if you have these arcs running through the tube, then the flip cobordism actually induces the identity map. So that means that with this picture, you can sort of get rid of the flip because this like flip induces the identity. So now you just have like the cylinder on K with this extra tube that's now orientable because we've gotten rid of the flip, and then the arcs are going through the tube. So now we'd like to do neck cutting, but there is one slight problem, which is that our arcs are sort of still going through this tube. So like originally when we wrote like the first version of this paper, we had to add an extra tube to sort of deal with this, like to get rid of this problem of the arcs going through the tube. But Ian Zemke reached out to us and showed us that that was not actually necessary. So he gave us this bypass argument. So basically, if you have your arcs going through this tube, there's like a bypass relation. So it's sort of in the region circled by this little blue loop. You can do a bypass argument to replace like the inside of that region with the sort of other like bypass arcs. And so you get to replace this upper picture with these two pictures on the bottom. And then you can do a grading argument to get rid of the picture on the right. So then you just are left with these arcs no longer going through the tube. And then you can do the regular tube cutting argument. So having completed some the arguments for the proof of our main theorem, let's now talk about some of the corollaries. So these corollaries are mostly also going to be analogous to the ones in Juhas, Miller, and Zemke's paper. So the first corollary I want to talk about is about non-orientable ribbon cobordisms. So a knot cobordism is called ribbon if it has no local maxima. So in particular, a ribbon concordance is a ribbon cobordism that's also a concordance. And so as an immediate corollary of our theorem, you can see that if there is an unorientable ribbon cobordism from K1 to K2, then the torsion order of K1 is bounded by the torsion order of K2 plus the non-orientable genus of the cobordism. And you can sort of see this because this is just immediate from the fact that like this means that there are no deaths. Another corollary relates to the band unlinking number. So the unoriented band unlinking number of a knot is defined as the minimum number of orientable or non-orientable band surgeries that turn the knot into an unlink. Then from our theorem, we can see that the torsion order also provides a lower bound for the unoriented band unlinking number. And you can see this just because if you have this cobordism that sort of goes from your knot to the unlink, then if you cap off some of the components of the unlink, you get that basically this unoriented band unlinking number can be seen as the number of deaths plus this unorientable genus. The other consequences I want to talk about are about the refined unorientable cobordism distance. So the standard cobordism distance between two knots is defined by the standard slice genus, twice of the standard slice genus of the connected sum of K1 with the mirror of K2 for the standard cobordism distance between K1 and K2. This is not a distance on the set of knots because concordant knots have distance 0, but it descends to a well-defined distance on the concordance group. So Juhasz, Miller, and Zemke defined a cobordism distance on the set of knots, that they call the refined cobordism distance, and gave lower bounds for it in terms of the torsion order in knot Floer homology. So we're going to do a non-orientable version of that. So for an orientable or non-orientable cobordism from K1 to K2 with little m local minima and big M local maxima, we define the norm of sigma to be the maximum of little m and big M minus the Euler characteristic of sigma. Then for two knots K1 and K2, we define the standard unorientable cobordism distance to be the minimum of the negative of the Euler characteristic of sigma, where sigma varies over unorientable connected cobordisms from K1 to K2 and genus 0 orientable cobordisms, that is concordances. And then for the refined unorientable cobordism distance, it's like that, but instead of taking the minimum of the minus the Euler characteristic, we take the minimum of this norm of sigma, which is like basically the genus with this extra, which also keeps track of the minima and maxima. So in this case, the standard unorientable cobordism distance is still going to be a distance on the concordance group, and the refined unorientable cobordism distance is a distance on the set of knots. So one of the consequences of our theorem is that the refined unorientable cobordism distance has a lower bound given by the difference between the torsion orders of K1 and K2. To see this, you can sort of directly see from our theorem that the torsion order of K1 minus the torsion order of K2 is less than or equal to the number of deaths plus the unorientable genus. And here, this is just because the maximum of M and order of K2 is less than or equal to the sum of M and the order of K2. And then you can run your cobordism backwards to get the torsion order of K2 minus the torsion order of K1 is less than or equal to little m plus this non-orientable genus, and you can put these two together to get these inequalities up top. Okay, so another thing that we did is we showed that the refined unorientable cobordism distance can be sort of made to be arbitrarily different from the standard unorientable cobordism distance. So to do that, we did some computations of the torsion order in HFK prime. Specifically, we computed the torsion orders for some knots which were connected sums of certain torus knots. So for the torus knots we considered were T, N, N plus 1 torus knots, and in this case, the torsion order of T, N, N plus 1 is the floor of N over 2. You can sort of see this by considering the Alexander polynomial, because torus knots are L-space knots, so the Alexander polynomial determines the knot-Floer complex. And in fact, like, you can also probably you can compute Tn n plus 2 and Tn n plus 3 this way as well, but we are focusing on Tn n plus 1. And then we want to sort of compute the torsion orders for connected sums of torus knots and their mirrors. So we also have these other formulas. So for the connected sum of K1 and K2, the torsion order is the maximum of the individual torsion orders, and the torsion order of the mirror is the same as the torsion order of the knot. So from here, we can conclude that for any fixed genus and positive integer m, there is a knot such that its standard cobordism distance to the unknot is gamma, but its refined cobordism distance to the unknot is at least gamma plus m. So it can be we can make it arbitrarily different. And the way you do this is by considering this knot, which is knots which are basically the connected sum of T2r minus 1 2r with the mirror of T2s minus 1 2s. The idea being that somehow the fact that you're taking the connect sum with the mirror is like sort of canceling out the sort of standard cobordism distance to the unknot, the standard unorientable cobordism distance to the unknot, but like not canceling out the refined one, right? Because the refined one, this connect sum actually gives you the maximum of the two of them. And then so basically what this is saying is that for gamma, you have there are cobordisms, cobordisms to the unknot with basically unorientable cobordism, unorientable genus gamma, but any instantiation of this has to have at least m local minima. And so, yeah, I guess thanks for listening to my talk, and thank you to the organizers for inviting me.